that I released the practice exam finally last week. And I was asking the few of you that were here before what you thought of it, but I'll ask the whole class now. If you've had a chance to look, what do you think? Does this seem a reasonable length? The midterm will not be more difficult than the practice exam. Okay, and of course we're going to finish covering the necessary material about integration to solve. I think it was the fourth problem, right? And you can probably piece it together, but we'll say some more rigorous things today. But by and large, it feels okay. Is that okay? Good, good. Right. So, where were we on Tuesday? I think we just reached the end of a justification of why we can take a parameterization of a directed smooth curve and express a contour integral along that curve as in terms of that parameterization, right? So we went through some computation to justify this, and this is it's about as far as we'll go for proof, what I said on Tuesday. But let's state the result in a precise fashion at least. Okay. So we basically ended Tuesday justifying the following. Okay, so let's let f be a function continuous on the directed smooth curve gamma. Okay. Then, if z of t for t in the interval a to b is a correctly oriented smooth parameterization of gamma, we have the following, right? And this is what we spent the end of Tuesday justifying, that when we look at the Riemann sums that define this contour integral and the following real integral, the integral from a to b of f of z of t times z prime of t dt are equal. Right? We're working in Riemann sums, and we did some algebraic manipulations and some differential approximation to show that when we take the limit with regard to partitions, that is to say, we take the limit of Riemann sums, that we have an equality here. That essentially, this is really great, right? We can just, if we come up with a smooth parameterization of our curve, remember the condition that we have our parameterization is differentiable and one-to-one, right? We restricted the types of parameterizations that we want to look at, and it goes in the same orientation as gamma is drawn in the plane, right? There's a lot of technical conditions around these objects that are flying around, right, where we have like a directed curve, and then we have like a piecewise smooth curve, which doesn't have direction, and you know, we try to take care to, the reason we distinguish all these things is because we want to be able to just produce a formula that we can plug things into, right, and to make things work up to something, right, we have to make sure that our conventions are consistent throughout. Okay, so right, this is to say, we have this formula now, which is nice, right? I've taken this new object, a contour integral, and expressed it in terms of a much more familiar object, just an integral of a complex function on the real line, right? On a segment of the real line. So you can kind of think of this as recentering, like taking our contour gamma and straightening it out and looking at it as a segment of the real axis. Okay? That's a sometimes useful analogy. That's not exactly what's happening, but it's still useful to think of that sometimes. Okay. Okay. So, let's see. What you can deduce right away is a corollary. Say we have Z1 of t and Z2 of t. Oh, sorry, I guess I should say this in a slightly different way. If, let's say, Z1 of t smoothly parameterizes gamma for t in the interval a to b, and Z2 of t also smoothly parameterizes gamma for t in some other interval, c to d. Then what we have is that the parameterized interpretations of the contour integrals are equal. Okay, this is something that we would like very much to be the case. Z1 of t times Z1 prime of t dt is equal to the integral from c to d of f of Z2 of t times Z2 prime of t t. Okay, so and I want you to think about this, how to deduce this corollary from this theorem, and maybe that'll be part of the next problem set. Just meditate on this for a little while. Yeah, but whenever we define an operation, we would like it to be invariant to any arbitrary choice we make, right? We had some discussion about, yeah.
Wouldn't it be slightly more correct to say that instead of using t for z2, you could use another parameter?
Slightly more correct.
Because isn't it arbitrary what parameter you use?
Yeah, I mean,
Okay.
that's definitely true, because the result of this is a number, right? It's a
Yeah,
complex
yeah.
number, and so is this. So it is immaterial. I could put an S here. I like. But by the same token, I could also put a T here.
Yeah.
Should I put an S here? Let's say both.
Just I'm thinking, because like T is in A and B, and T is also in C and D, but it's the same path, so
Right. So when you evaluate these,
yeah.
you're taking T to B from A to B in here,
Yep.
and you're taking T to B from C to D in here. I think I'll leave it because this is a common notation. You're right, you could write it differently. I could put an S or a R or a, who cares, I could put like a C there if I wanted. But, why do people make that choice in all the textbooks of complex analysis that I've read stated this way? Why? Maybe it's the only thing I can come up with off the top of my head is to highlight that you need to be able to recognize what the domain of parameterization is all the time. It doesn't matter what the variable is called. In fact, we'll give it the same name. It doesn't matter. You have to pay attention to the domain of parameterization. Maybe that's why. I'm not sure.
I think T is like the same variable, but just in the left integral
It's taken in.
along A and B.
Yeah, exactly. It's taken in a different domain. So, yeah. I think I'll leave this just because of convention.
It's just like drawing a picture of it, right? You'd have like some gamma, and then at the beginning you have Z of T equals A at the initial point, and Z1 of T equals A, and Z1 of T equals B, and then that would be identical, like the endpoint would be the same for Z2 of T equals C, and Z2 of T equals D, right?
Well, so remember, A, B, C, and D are values that T can take, so what you said was not consistent with what you were saying. Okay, so let's just leave it at that. I think we're okay. This is just a notational point, right? Okay. So, right. As I was saying, any construction we make, we would like to be independent of an arbitrary choice that we make, right? And as we were discussing, we had some small discussion about how you can come up with arbitrarily many, or infinitely many different ways to parameterize the same curve, right? So it's an arbitrary choice on our part what the parameterization that we choose is, as long as it's smooth, right, and one-to-one. So, and there's still infinitely many of those in all the cases that we'll see. So this is kind of a foundational result, that it doesn't matter what our arbitrary choice is. This is kind of a crutch that our understanding leans on, choosing some parameterization. And if I have a different understanding than you of what the curve gamma is, and we parameterize it in different ways, we'll get the same answer, no matter how we parameterize it. Okay? Okay, so let's do an example. Knees don't have 4 legs. So let's let C sub R, sorry, be the circle of radius R centered at Z naught. Traversed once in the counterclockwise, which I'll commonly abbreviate as just CC direction. let me ask you to then compute the integral around the contour C sub r of the function z minus z naught to the n dz. So this seems like a fairly innocuous example, right? Our contour is something that we're quite familiar with, a circle, and this function is fairly simple to write down, right? It turns out that this will be something that will be a vital tool for us for evaluating arbitrary complex contour integrals. So put a star next to this in your notes. This will be extremely useful to us both in our theoretical investigations and in practically computing things. Okay, so, but for now, what ingredients do we need in order to compute this integral? Based on our discussion to this point. Yeah, we should try to parameterize C sub r, right? So, who can suggest a parameterization of C sub r? Yeah.
We can have, sorry, we use C of t for parameterization.
Yeah, again, so notation, whatever you like. I default to, I used Alforce when I was in undergraduate, and I usually say gamma of t, because gamma is the curve. Our textbook uses z of t. Whatever you like is fine by me, whichever notation you choose. But yeah, let's say, so z of t. So let's write down what we're saying. Parameterize C sub r by z of t is,
So we can write C0 plus R times t by t, or t going from 0 to
yeah, great. So I'm very, a fully complete and correct answer, right? Remember, when you specify a parameterization, you have to specify the domain that your parameter t takes values in. Okay, great, thank you. Right, so, of course, if convince yourself of this by just plugging in some values of t here, and see that this actually gives you a circle of radius r centered at z naught. Yeah.
Should both 0 and 2pi be inclusive, or should only?
So good point. And if you look back at our discussion of simple closed curves, we allow for non-injectivity at the endpoints. This makes certain things nicer. So like, if we had just taken 1-to-1 as the requirement of our parameterization, then yes, we would have to exclude one of the endpoints. But we bake that into the definition of simple closed curve, just because some things shake out nicer, as you'll see. Okay, good. Okay. So, great. We have a parameterization. Now we can just plug into our formula from the previous theorem, right? So this is to say the contour integral around C sub r of z minus z naught to the n dz. Oh, sorry, I guess I forgot to say. For integer n, right? Can say something for real n or even complex n, but we haven't gone that far yet. And that's kind of a side exercise, something of historical interest, but not necessarily, doesn't come up much in our applications. Maybe I'll, whenever I'm lecturing, I'm trying to think of some interesting problems for the next problem set. Maybe we'll talk about what it means to exponentiate by a complex number in the next problem set. Maybe. We'll see. Okay, so in any case, let's just apply our formula here, right? So if we want to plug in our parameterization, now our bounds of integration just become the domain, the endpoints of the domain of the parameterization, and we plug in for z our parameterized formula, z naught plus r e to the it minus z naught to the n dz.
Don't we have the non-primitive t also?
Oh yeah, I forgot the derivative. Thanks. What's the derivative of our parameterization?
I r e to the it.
Yeah, the constant z naught drops out, and we just use the chain rule to get I times r times e to the it. I times r e to the it. Good. Easy.
And dt, right?
Right.
T, yeah. Good. Okay. So, these cancel, right? So I'm just raising r e to the it to the n times I r e to the it. So what do I get? I just get I r to the n plus 1 times e to the I n plus 1 t dt. So I and r to the n plus 1 are just constants, right? R is just the radius of my circle, integrating with respect to t. So I can pull these out. I times r to the n plus 1 times the integral from 0 to 2 pi e to the I n plus 1 times t dt. Okay, so if I'm restricting myself to consider n to be an integer, where do I go from here?
Well, you can integrate.
Say it again.
You can like integrate e to the I n plus 1 t to get 1 over I n plus 1. So yeah, 1 over I n plus 1 e to the I n plus 1 t. And then if you evaluate that at 2 pi or 0, you get an integer multiple of 2 pi for one of them, and then e to the 0 for the other.
Assuming it is not negative 1.
Exactly.
Oh, yeah.
That's the key step. There are two cases, right? We can't divide by 0, so we can do our standard anti-differentiation of this formula in general when n is not equal to negative 1. When it is equal to negative 1, we'll get a slightly different result. Okay, good observation. So let's see, let's first carry out the computation when n is not equal to negative 1. And it's not equal to negative 1. Okay? Then we can proceed as quote-unquote normal, right? We have, oh sorry, I have my constant up front, of course. I times r to the n plus 1 times the integral of from 0 to 2 pi of e to the I n plus 1 t dt, which is just equal to I times r to the n plus 1 times e to the I n plus 1 t divided by I n plus 1 evaluated at 2 pi and 0. And here I've technically I've done a u substitution, right, where I just have a constant come out from differentiating u. I set u to be equal to I times n plus 1 t. Okay, good. Okay, so my i's cancel, right? And what do I get here? R to the n plus 1 times e to the I n plus 1 2 pi divided by n plus 1 minus e to the 0 divided by n plus 1. Well, what's e to any integer multiple of 2 pi I?
0.
Is just it's just 1.
E to the 0, yeah.
Right, e to the 0 is just 1. So we get that these cancel, right? This goes to 0, and we just get 0. Okay. So, secondly, interesting. See what happens when n is equal to negative 1. Right? The only other
It's because it's like a closed loop with the same endpoint.
Say that again?
Is this equals 0 because it's like a closed curve with the same starting endpoint?
So when n equals negative 1, our curve is the same, right?
So what's
What are we recording? That's a really good question. And you might, I'm glad you asked that, because answering that question will lead us to a lot of the results about integration that we're going to determine. Right? Remember, I told you that recording where a function has poles allows us to come up with a really rapid formula for computing definite integrals of it around a contour.
so is it like if it's like a closed contour and it's not in a pole, then it's 0?
Well, now think about this, right? So for positive n, you don't have a pole at d0, right? And for negative n, not equal to negative 1, you have a pole of higher order. So you still get 0 when you integrate a closed curve around it. But when we have a pole of order 1, or sorry, no, when we have a different type of singularity, right? There's some different behavior at n equals negative 1. Okay, so I can't give you a complete answer right now, right? Because we still have to build a little more machinery. But I'm really glad that you asked that question, because answering that question is what we're going to be doing over the course of the next week or so. Okay, but for now, let's satisfy ourselves by just computing this directly and see what we get. Okay. Right. So we get the integral from 0 to 2 pi of what's my integrand again? Oh, sorry, I keep forgetting the constant up front. I times r to the negative 1 plus 1, 0, times the integral from 0 pi of e to the I times 0 times t dt. Or in other words, I times the integral from 0 to 2 pi of just dt. Evaluate this right away. It's just 2 pi I. Okay. Very, very strange that when our integrand has a simple pole at z0, then we get a non-zero value for the integral of a closed contour which contains or loops around that pole. This is seemingly very strange, but what we'll eventually see is that when we're dealing with functions that are analytic at all but a finite set of points, we can compute their integrals along closed contours based on this fact that we just computed. And how will we do that? Just as a preview, we'll take if it's a rational complex function, we'll produce its partial fraction representation. Okay? And if it's not necessarily a rational function, but it still has poles, then we will have to do something similar to in Calculus 1 when we represented a function as a Taylor series. But now we will allow negative exponents. It's called a Laurent series. Okay? So I just gave you a sweeping view of what we'll be doing for the next few weeks. Okay? I just said a lot in a very few sentences. So don't feel like there's a lot of information there. It's okay. Not everything is clear yet. But that's where we're headed. That's in our purview. Okay. Okay, so, right. So far we've been talking about only a single directed smooth curve. Let's talk about contours in general, right? I've only mentioned gamma, single gamma so far. Now I'm going to make precise this thing that I've been saying since we started talking about contours, where we use this formal sum of concatenation of directed smooth arcs to, we use this notation of addition because we can split an integral up across a contour capital gamma across the sum of its smooth pieces, right? Okay, so. Right, if gamma is a directed smooth contour with, in our notation from before, gamma equal to gamma 1 plus gamma 2 up through gamma n. Let's say it has n directed smooth curves as pieces. Gamma I a directed smooth curve. And take capital F. I don't know why I use a capital F here. Let's stick with lowercase f. Just because capital F usually means n derivative or something. So if we have a continuous function f, and f continuous, on gamma, then what we have is that the integral over the contour gamma of f of z dz is equal to the integral along gamma 1 f of z dz all the way up to the integral along gamma n f of z dz. Okay, we also make the convention, and if the contour gamma is a single point, we declare by fiat that the integral along gamma of f of z dz is equal to 0. Here, remember we made this this is part of our definition of the contour, right? We allowed for a contour to be a single point. How do we parameterize a single point? Yeah, it's a constant function, right? Z of t is equal to some constant, the point, for all t. Whatever interval you like. Okay?
Is a point considered closed?
Is a point closed?
Because if it is, you can think of it as a closed curve with no poles. So it should be 0.
What does it mean for a curve to have poles?
Yeah, good question.
A point is closed in the plane, right? Because take a neighborhood around any point in your set, which is just a single point, and it will contain at least one point in the set and not in the set. Namely, it will contain the point itself, and it necessarily contains some other points not in the set. Okay. Now, if you go on to study topology in general, you will encounter some spaces where points may not be closed, which arise naturally in other settings, but I won't go into that now. Topology is weird though, in a good way. Okay, so let's do another example. Let's compute this integral of a function that we worked with in our last example, but now we're going to change what gamma is. We're going to change our contour. Where gamma is the circle E minus Z naught modulus of is equal to R. Traversed twice in the clockwise direction. Okay. So, we would like to apply our last theorem and this definition, right? That is to say, we can essentially use, excuse me, there's lots of ways to do this, but let me suggest a way that kind of ties into our last example. Okay? So, let's consider consider gamma equal to the sum of gamma 1 and gamma 1, where gamma 1 is parameterized by z of t is equal to z naught plus r e to the negative I t, t between 0 and 2 pi. Okay, so this is, why did I choose to do this? What I'm doing is taking my contour gamma, which is, let me draw a picture here. Now I'll say Z naught is here. Okay, come out of radius R. Okay, so, sorry, we're going in the other direction. Should have drawn it in the other way. So we go like this, this. I traverse it twice. So I break it up into two contours, two smooth, smooth curves. Gamma 1 is just traversing the circle once. And then I do that again. Okay, so why do I do this? Because gamma 1 is almost exactly the same as CR from our last example, right? It just has this negative sign. So, hypothetically, what I would like to do is draw some connection between the curves CR and gamma 1, which is parameterized by this. Yeah?
Could we not just use the properties of integrals along contours to say that because it's clockwise, it's negative to counterclockwise?
Yeah, we haven't proven that yet.
Oh.
So I'm trying to demonstrate this now. But yes, exactly. So the takeaway is that it's like, so really another way to write this is 2 times gamma 1 or 2 times negative C sub r, right? C sub r with the negative orientation, the opposite orientation. And this curve arithmetic that we set up formally matches what we get for the values of the integrals. That's what this example is supposed to illustrate. So yeah, I'm glad you said that. That's exactly the point of what we're going to do here. But let's parameterize it, or we have parameterized it. Let's make the computation explicitly and verify that we get negative 2 times the result from our last example. Okay? Good. All right. So what do we get here? I'll take the integral over gamma of 1 over z minus z naught dz is equal to the integral over gamma 1 of z minus z naught dz plus the integral over gamma 1 of 1 over z minus z naught dz. Now I'll apply the first theorem of the day and plug in my parameterization and its derivative to compute these contour integrals explicitly. Yeah? Okay? So, we go from 0 to 2 pi. Well, first of all, let me just simplify my computation slightly. I get the same thing here, right? So this is just 2 times the contour integral, right? So I'll say equals 2 times, and then I'll plug in my parameterization. So 1 over z naught plus r e to the negative I t minus z naught times the derivative, right, which is just negative I r e to the negative I t dt. Okay. So all together, we get a lot of cancellation here. We get negative 2I out front times the integral from 0 to 2 pi of just dt, right? Our z naughts cancel, our r's cancel, pull out a negative I, and then e to the negative it divided by e to the negative it is just 1. So in conclusion, we get 4 pi I, negative 4 pi I, which you'll recall is just negative 2 times the integral along CR from our first example of C 1 over z minus z naught dz. Right. Exactly the conclusion the fast way to compute this, right? It's just good to check these things explicitly. This holds in general. That is to say, firstly, if we take the integral along the negative of a contour of a function f of z, which is continuous along that contour, this is just equal to the negative of the integral along that contour of the function f of z dz. And in addition, our usual rules of integration apply here. That is to say, contour integrals are linear, right? We can split up sums and pull out constants. Okay, so let me just say, how should I write this? The contour integral over gamma of a times f of z plus or minus b times g of z dz is equal to the contour integral over gamma, is equal to a times the contour integral over gamma of f of z dz plus or minus b times the contour integral over gamma of f of z, g of z dz. Okay. Just like integrals, any type of integral that we're familiar with up to this point. Oh, okay. So, right. We're going to take breaks now. So let's reconvene in 5 minutes. Yeah. So I promise that we're closing in on some really interesting stuff. I know that this might seem kind of a little dry. I understand if you don't appreciate this material as much, but it's necessary foundation that we need to go through. So, any good Halloween plans this weekend? A resounding no. Okay. Well, likewise, I have no plans.
I had plans for Halloween. I was going to go to a concert with my brother. I was going to see Judas Priest with him.
Oh, cool.
Well, it was gonna be great. And then one of the guys from Judas Priest had like a heart condition. But yeah, he's okay.
Cool.
But they had to delay all the concerts and stuff, so now I have no plans.
My roommate and I had to scavenge our apartment to find like costumes to wear tonight. And we ended up making, we took some like white t-shirt and made it like tore holes in it. He's dressing up as like a Royals person.
Okay.
Yeah, and then I think I'm going as a professor.
Okay, I went as a professor last year. It was my first year here, so I was like, oh, you know, I might not seem very professorial, but today, it's the real deal.
My other roommate's going as a business major.
Okay. Really getting in there on the social commentary, huh?
Rough.
I'm gonna go as a not stressed out college student in hopes it becomes real.
Ah, yeah, one of those costumes you don't take off.
Yeah.
That's good. That's good. I'm about to move apartments, so maybe when my roommates are out, I'll take the opportunity to pack. That seems like a sufficiently spooky Halloween activity.
Fun Halloween plans.
Yeah, see what is lurking in my home.
Make a horror movie out of it.
Yeah. I guess you could. If I don't come back on Monday, you know what happened.
You find the old sandwich from like 4 months ago on your desk.
No, I think my room has the least mice in it, so there's probably no sandwich left in there.
Speaking of horror stories, in the past like 3 nights, at like 1 a.m. or something every night, I hear something like skittering around in my kitchen. And every time I walk in there, it's like all the way in the back. And when I walk over there, I can't hear it anymore and I can't find anything. It's the worst.
Oh, whatever it is, that's a pretty good game plan.
I think it's like a cockroach or something, but it's like too loud for that. But I don't want to think about what that means in size. So I'm just...
If that's okay.
Trying to get a big one.
My next door neighbors, I guess across the hall, they had a rat problem. We never had that.
Oh, I got a house.
Okay, mice are not as bad as rats. That's a plus.
My brother used to have rats. He used to go to BC, he used to have rats, and he would stay up at 3 in the morning and take airsoft guns and shoot me at him. And he had good aim.
I bet after he moved out, he had great aim.
It's awfully tempting for somebody to be right there.
You know, they have that bread smell, that Subway
Yeah.
bread smell.
Yeah, every time I walk in.
That's the best part of Subway, just smelling it as you go by. Okay, so let's start again. So we've been kind of gentle so far, right? We've only really dealt with somewhat broad and easy to compute examples. Let's look at something that's computable, but will take a little bit of work. And the reason for this is because when we get to the analog of the fundamental theorem of calculus, I want you to appreciate it fully. Right? So it's like, oh, that was a lot of work, but I won't have to do that under the right circumstances. Okay? Okay, and also this illustrates the fact that, again, integrability is a much laxer condition than analyticity, right? And again, we're building to a point where when we take the integral of an analytic function, we'll be able to say some very nice things. And we've been able to say some nice things so far, but if we assume our integrands are analytic, then we'll be able to say even more and compute even faster in certain circumstances. But for now, let's see what we have to do when we're not in those nice situations. and we ask you to compute the integral along gamma of the conjugate of z squared, dz. Where gamma is pictured below. Okay, and this is similar to some contour that we looked at before. We'll say this point here is 2 plus 2i. And this triangular contour that breaks up into smooth directed curves, gamma 1, gamma 2, and gamma 3. And we'll say gamma is equal to gamma 1 plus gamma 2 plus gamma 3. Okay? So, at this point we're just applying definitions, and like I said, this is slightly unpleasant, right? We have to come up with 3 separate parameterizations, one for each of these. And why is that? Why can't I just come up with a single parameterization? Because remember, I restricted the type of parameterization I want. I can't smoothly describe taking this right angle turn, right? I can't describe that with a single function in a way that is differentiable at this point, right? And the reason, now it should be clear why I insist that my parameterizations are differentiable. So I have this nice formula where I can translate a contour integral down to the real axis, right? It depends on the derivative. I want my pieces that I break up into to be differentiable. Okay? So, right. First, by definition. The contour integral over gamma of z bar squared dz is equal to the integral over gamma 1 of z bar squared dz plus the integral over gamma 2 of z bar squared dz plus the integral over gamma 3 of z bar squared dz. Okay? And we parameterize gamma 1, gamma 2, and gamma 3 as correspondingly z1 of t. Remember, we had this discussion about how to parameterize a line in a way that we can do it for any 2 points, that we can parameterize a straight line between it. We went over that on Tuesday, but here it's pretty clear what to do. We just let it equal t from 0 to 2, right? It's just the parameterization of gamma 1. Okay. Now, let's parameterize gamma 2 as follows. 2 plus t times I for t between 0 and 2. Now, remember, in this example, we did a similar example to this where I asked you to parameterize this contour over a given interval. But now, we can choose whatever interval we like that is convenient for us to write down quickly, right? I'm not putting in restrictions on how you, in what time intervals you take these pieces, because we just showed that it doesn't matter, per summand here, what time intervals we choose, right? So this is just an artifact of me choosing the fastest thing that I can think of. Okay? You don't have to do that, right? This is the whole point of the independence of the integral on the parameterization chosen. But, I don't know. That's, in some point of view, that's what mathematics is all about, trying to do things with the least amount of work. Right? Okay. I know that's not a universal philosophy, but it's sometimes motivates a lot of things in mathematics. Okay. So for gamma 3, I'll choose the parameterization as follows. Negative t times 1 plus I in the interval where t runs from -2 to 0. Okay? Again, you can verify for yourself. Either start with the general method for parameterizing a line that we did in class together on Tuesday, or just take my word for this and plug in some values of t and see what you get. At t equals -2, our start point, we get this point here. And then at t equals 0, our end point, we go back down here, right? And you can check that any t gives you a value on this line as well. Okay, so this is kind of the thing of sweeping under the rug, right? This is something that you have to practice on your own. Coming up with parameterizations quickly in a way that makes sense to you. And I'm just putting some stuff on the board and being like, this works. But you know, everybody thinks differently, so work on that for yourself to see how you like to parameterize things in a way that works for you.
So just a question,
Yeah.
parameterization, so 2 plus 2i in parentheses times 2 minus t, from t being from 0 to 2, would that work?
Okay, so what you said again.
So it's 2 plus t in parentheses times 2 minus t in parentheses from 0 to 2 for t.
Okay, you should verify that.
Because it's initial point minus, like the way you.
So it's linear, right? It only has a t in it. It's not any t squares, and your start and end points are the same. Then yeah, it should work. But I'm not gonna write that out, but verify that. Okay. So now we just evaluate. Each piece separately. Okay, so let's take first the integral along gamma 1 of r squared dz is equal to the integral from 0 to 2 of t bar squared times t prime dt. Okay, this is a kind of silly thing that I wrote. T is a real number, right? What's the complex conjugate of a real number?
Itself.
It's just itself. Yeah, we just get t back here. And what's the derivative of t with respect to t?
1.
It's just 1. Yeah, so this boils down to the integral of t squared from 0 to 2. Okay, and it's just 8/3. Okay. So the integral along gamma 2 of squared dz is the integral again from 0 to 2, right? Just looking at our domain of parameterization for d2 that we happen to choose of the following. The conjugate of 2 plus ti squared times the derivative of 2 plus ti dt, or in other words, the integral from 0 to 2 of minus 2 minus ti squared times I dt. Okay, so what is the integral of 2 minus ti squared times I? Tell me how to compute that. Yeah, so technically it's a u substitution, right? Because we're integrating a squared function with something inside. And of course I is a constant, so that just comes out, right? So we get our constant I out front, and we let u be equal to 2 minus ti. What's the derivative of 2 minus ti? Negative I, right. So that means we're going to divide by negative I our final result, right? Okay, and then we just have a u in here. What's the antiderivative of u squared? Is u cubed over 3, and I'll just plug u back in as we go. So evaluated at 2 and 0. Okay, here my i's cancel, right? So I get what do I get in total? I get negative 8 thirds. Oh no, sorry, skipping ahead. Negative 2 minus 2i cubed divided by 3 plus 8 thirds. Okay? That is to say, I plug in a 2 here, I get 2 minus 2i cubed divided by 3. And I plug in a 0 here, then I just get 2 cubed divided by 3. Minus, minus. Okay, almost there. Now we just have to compute the contour integral for gamma 3 to get the total contour integral along gamma, capital Gamma. The integral along gamma 3 of z bar squared dz is equal to the integral from negative 2 to 0. Remember, I just erased that my domain of parameterization for gamma 3 was negative 2 to 0. Again, an arbitrary choice by me, just to what I saw. Okay. And then on the inside, we have negative t times 1 plus I conjugate squared times the derivative of my parameterization, which is just negative 1 plus I. Okay? Negative 1 plus I. dt. Okay, so what does this give us? all together, bring the negative out front. We get a negative out front. Integral from negative to 0 of t squared times 1 minus I squared times 1 plus I dt. And I just pulled the negative out from here. Okay, so most of these are constants, right? I'm just integrating t squared again. Okay, so altogether, what does this give me? Negative 8/3 times 1 minus I squared times 1 plus I. Right. Sorry. Standard, good. Right, I have a negative 2, and I'm subtracting the lower, but I have a negative out front. Negative, negative, negative results in a negative at the end. Okay? Alright, good. So, all these together give us the value of the contoured integral along the gap of this continuous, but as we have stressed before, certainly not analytic function. Just add up all our computations, right? Plus negative 2 minus 2I cubed over 3 plus 8/3 plus 8/3 times 1 minus I squared times 1 plus I.
There should be a negative, right?
Yeah,
Not a lot, yeah.
yeah, good. I left that out of my notes. Okay, so if you take the time to simplify this, I don't know why you would, but what you get is 16/3 plus I times 32/3. Okay, again, nothing all too hard here, just kind of laborious, right? We would like it to be the case that we could just, even though contours can be any, well, many different crazy shapes, we would like some analog of the fundamental theorem of calculus, where we can find some antiderivative and just look at the value of the antiderivative at the endpoints of our contour. Right? If our analogy of being able to integrate along a contour as being roughly the same under the right conditions as integrating along an interval in the real numbers, then we should hope that some form of the fundamental theorem of calculus traverses this analogy as well. Okay, so let's see what we can say. Oh, sorry, I nearly forgot. So, did any of you take calculus 2 here at Northeastern? No, okay. So, when you did study the material of calculus 2, wherever you did, how much time did you spend talking about bounding integrals? That is to say, it is sometimes the case that we can't compute an explicit antiderivative. We can numerically approximate things, though, in those cases very often. And in fact, we can, by hand, compute some fairly reasonable estimates or bounds on those integrals? How much time did you spend talking about that? None. No, I'm seeing a lot of no. No head shakes. Okay, so, well, I'm proud to say that we spend a significant amount of time covering that at Northeastern in Calculus 2. I think that's a really cool topic. But we'll do some of that here right now. Sometimes we don't have to know the precise value of an integral. In many applications, we just want to know that it doesn't exceed some value. So let me tell you a few theorems. And if you go back and dig into, I'm sure, whatever Calculus 2 textbook that you might have lying around has this somewhere in it. There are real analogs of this. Okay, so these are just generalizations of some of the content I think you should have seen in Calculus 2, not to disparage any of your previous instructors. Okay, so let's suppose the following. Suppose we know f of z is continuous on gamma and the modulus of f of z is less than or equal to some real number m for all complex numbers z on the contour gamma. Okay? Then, any Riemann sum so I should say associated to Pn satisfies the following. Now if I take the modulus of, if I take the modulus of my Riemann sum corresponding to partition Pn, then what I know is that this is less than or equal to the sum of the moduli of the summands. Okay? So really I just moved the modulus sign inside the sum. And remember the modulus sign breaks up across products.
Triangle inequality.
And this comes from the triangle inequality. Yeah, exactly. Thank you. The triangle inequality. Good. Now, if we know that f of z is bounded by the real number m, then we could substitute that in here to get another inequality past this, right? So this in fact is, this term is less than or equal to, I'll just pull out the constant m if I were to replace the bound everywhere where a function value appears. Remember in our definition of Riemann sum, the points ck all lie on the contour gamma, right? Okay, so, right, what do I need to say here? M times the sum from k equals 1 to n of the modulus of delta z sub k. Okay. Good. So, then note that the sum of the moduli of the delta zk's is less than or equal to the length of the contour gamma. Remember, we defined in lecture on Tuesday, or perhaps it was last Friday, the length of a directed smooth curve is just the integral of the distance formula, essentially. Right? And the length of a general contour gamma is just the sum of the lengths of each of the components of capital gamma. Right? So when you think of it that way, remember that delta zk is just the line segment between zk and zk minus 1. It's the shortest path. Right? So anything crazy that gamma does will be longer, at worst. It could be just, gamma could just be a straight line in each of its smooth components, but it will always be greater than or equal to. The length of gamma will always be greater than or equal to this. Okay? So, right, and which really, again, is because of the triangle inequality, right? It's a consequence of the triangle inequality. That's worth noting, okay? Again, because of triangle inequality. I debated whether to say anything about this or not, and I feel like the way the term has been going so far, I usually say something offhand about a random related topic. This is under the condition that we took so much time to define what gamma is allowed to be, right? Because these size estimates don't necessarily hold when we allow non-rectifiable curves to be in the class of contours that we're considering. So what is a non-rectifiable curve? Let me just make a note of this. This holds when contour gamma is rectifiable. What does rectifiable mean? It means that it actually has a finite length. Right? That is to say, you can actually straighten it out into a line and it becomes a finite thing. Non-rectifiable curves, we've seen one already. The boundary of the Koch snowflake. Right? This triangle, this successively finer triangle thing that we built. If we take the boundary of that, that's a non-rectifiable curve. Because if you straighten it out, it just folds in on itself infinitely.
Is it true for every fractal?
That's a good question. I don't know the answer to that. My intuition says yes. Yeah, of course, you would have to say something like every fractal of dimension less than 2. Then, beyond 2, you'd have to say, make the relevant definition of rectifiable for surface and higher dimensional thing. But yeah, in spirit, that's the right thing. Yeah.
So just like off topic kind of, but would a rectifiable curve, like would the Koch's snowflake have a finite area?
Say that again?
Does the Koch's snowflake have a finite area? In other words, can rectify.
The question is, what do you mean by area?
Area enclosed by the curve?
Okay, how do you compute that?
Good question.
Okay, so I mean, one thing you might try to do is take a double integral in the region bounded by it of the constant function 1. But then that method of finding the area fails because the curve is not rectifiable, the boundary is not rectifiable. Now, that's not to say.
You would do it maybe geometrically by using triangles?
Yeah, so that's interesting. I don't know the answer, if the answer is positive or not. My intuition tells me that you can probably define a notion of area that gives you a finite area for the region bounded by the Koch snowflake, but it's probably not consistent with. That is to say, I think there's more than one possible definition and they don't agree. That's what I think. I don't know.
It could be like an infinite sum of each of the triangle areas, which I feel like would converge to.
That's what I was thinking.
So yeah, I mean, this is a good question. I don't know the answer. You should try to resolve that over the weekend. Everybody said they don't have any Halloween plans. try to do this over the weekend.
Do you know whether non-rectifiable curves, I guess area in the sense we just tried to define it, because it's like in geometry you have Gabriel's horn, which has like a finite area of a.
Yeah, so right, that has a
perimeter, like the infinite perimeter.
it has an infinite surface area and finite volume.
Yeah, and for this guy, like an infinite perimeter, but maybe a finite area.
Again, these are all questions. Some of them might be answered, but I don't know the answers. So think about this. This is good.
When you're making the snowflake, do you just like arbitrarily choose how large the triangles on the side of the original triangle are?
Well, since you're taking the limit, it doesn't matter what size you.
Does that make sense?
Yeah, for the length at least.
Yeah.
This is something you would have to consider when you're trying to compute the area.
There is a finite area, it says.
Oh, great,
Yeah, it's pretty simple, it's only a quadratic.
great. So that matches your intuition, right? A thing in the plane, a quadratic expression for area. Okay, so there you go. Maybe I've been thinking about alternative ends of the term. I don't know, like the possibility of maybe having like presentations or projects or something. I know that that's like a massive departure from what the syllabus is, but I was going to ask everyone what they thought. Eventually, it seems now more an apropos time than has presented itself yet. I haven't really thought of the structure of what that might look like, but maybe we'll send a poll out. I mean, I would be fine doing a normal final exam too, but it just seems like we've had some interesting topics come up. Maybe you'd like to dedicate more time to looking into this further instead of just taking an exam, but it's up to us. You know, this is what I love about a class this size. So we can do whatever we want. Okay, so good. We'll talk more about that later. Let me fill the last 10 minutes with, let me get this out about the bounds of an integral. Okay, so, right. Okay, so we have this inequality, which now implies that we can take our far left-hand side, the sum from k equals 0 to n of f sub c times delta z sub k is less than or equal to m times L of gamma, right?
Is there any arbitrary choice why you picked k equals 0 now? Is it?
No, I made a mistake. Sorry. Right. So now, take limits as the mesh of our partition goes to 0 that's how we get an integral from a Riemann sum. We take the limit as the mesh goes to 0 over partitions. And then we get the following theorem. The modulus of the contour integral along gamma of f of z dz is less than or equal to m times the length of gamma. Of course, let me just restate my assumptions. If for all z in gamma, f of z is less than or equal to m, and yeah, sorry, right. The modulus of f of z, good. And f is continuous on gamma. Okay, in particular, the modulus of the contour integral along gamma of f of z dz is less than or equal to the maximum of the modulus of f of z for z in gamma times length of gamma. Okay, so the point here being that this bound m doesn't have to be so abstract. If I understand my function f fairly well, I can just see what its maximum value, the modulus of its, the maximum modulus of f is on the curve gamma. And I can use that as my bound, right? If I happen to understand my function really well, right? I could be just handed some bound from some other circumstance, but you know, I can also give it an explicit form of the bound if I understand my function well enough. Okay, so I think we have time for one example of how we might do this. So let me ask you to find an upper bound the modulus of the integral along gamma of e to the z divided by z squared plus 1 dz where gamma is the circle of radius 2 centered at the origin, traversed once counterclockwise. Okay, so firstly, what are the ingredients we need to come up with a bound according to our theorem?
The e to the z over z squared plus 1.
Yeah, yeah, so that's one thing we would like to find, the maximum value of this function here on the circle of radius 2 centered at the origin. And what else would we like to know?
The length of that circle.
Yeah, right, or the length of that contour, and since it's a circle, we can just use the circumference formula, right? Okay, I think that's a great place to start.
Is the fact that it goes counterclockwise relevant here?
No, the length would be the same, whether you, it's just the number of times you traverse that determine the length. And if I had said twice, it would be twice the circumference. Okay, so, good. So yeah, it has no bearing on computing the length, right? That is to say, in terms of the terminology that we laid out on Tuesday, we're computing the length of the undirected smooth curve, or I forget what I said. Right? We're forgetting the orientation of gamma when we compute the length. But this does, of course, matter for the computation of our integral, but we're taking the modulus also, right? So we can actually make a size comparison. Because in general, the integral will output a complex number. Okay, so as we were just saying, first note, L of gamma is just 2 pi times the radius, 2. 4 pi. That's nice. Okay, now, so, found the function. We'll assume, as usual, that z is equal to x plus iy. Then, what we could say about the modulus of e to the z, of course, this is just the modulus of e to the x times the modulus of e to the iy, which is just equal to e to the x, right? The absolute value of e to the x. E to the x is always positive. Which is is less than or equal to e to the 2 for the modulus of z is equal to 2, right? The maximum value that this can assume is x is equal to 2, right? Okay. Now, let us be a little tricky here. I'm going to derive a bound for the denominator in the following way, using the triangle inequality. Okay, so first, note that the modulus of z squared, of course, is equal to the modulus of z squared, right? Which I can also say is equal to the modulus of z squared plus 1 plus negative 1. Yeah? I haven't done anything illegal yet. Now I'll use the triangle inequality. Right? So this is less than or equal to the modulus of z squared plus 1 plus the modulus of negative 1, which is equal to the modulus of z squared plus 1 plus 1. Which altogether tells me that the modulus of z squared plus 1 is greater than or equal to the modulus of z squared minus 1. Okay? And this is, oh, sorry. The maximum value that this can attain. Oh, no, I'm sorry. This is equal to 4 minus 1, or 3 on the modulus of z is equal to 2, right? Okay, looks like we're over time. Sorry. So one last thing I'll say, and then we'll pick this up on Monday. This tells us that 1 over the modulus of z squared plus 1 is less than or equal to 1/3. Right? So I'll combine all this information to come up with a bound on the modulus of the integral. Okay? So have a good weekend. Sorry I went over. And I'll be sure to have your problem set 3s back to you on Tuesday before the exam. And I'll also send out the solutions to the practice exam before then. Okay?
I just gotta go take a midterm and I'm done.
All right. Good luck.